Okay, here we are again, talking about electromagnetism a little bit more. In the past week or so, we've discussed electromagnetism as far as charges are concerned and light. So now we're going to talk about a couple of rules, Wien's law as well as the Stefan-Boltzmann law. So let me remind you what the whole purpose of this past two sections are. We want to describe what light is, characterize it. What is matter? Characterize it. Then we also want to figure out what is a wave and what is a particle. These are how we describe the world around us. And there is a deep connection between light and matter, and that allows us to see, really, to understand the world around us. It is by this notion of the light and matter interaction that allows us to move around in the world and to participate in it. Now, there is a deep connection between temperature and light, as well as these two phrases that I talked about, Wien's law and Stefan-Boltzmann law. The simple phrases go for Wien's law. Basically, it goes like this. The hotter something is, the bluer it is. And then for the Stefan-Boltzmann law, it's the hotter something is, the brighter it is. All right, so the connection between temperature and radiation is a fundamental one. Temperature is basically the way we describe the average motion of particles. They can be atoms or they can be electrons. And when things with charge move, they radiate energy. In particular ways, as they bounce around, they are sort of defining the space that they're in. So the average value of this motion is an indication of temperature. They go hand in hand. So temperature is the average energy something has. So the more motion, the higher the temperature. And so this defines a natural temperature scale for us. Absolute zero is when we have no motion at all. Okay, so that defines a temperature scale that again is most natural. It is the Kelvin scale. 0 degrees Kelvin is where all motion stops. Now, previously, you have probably heard about the centigrade scale or Celsius, and you also are probably pretty familiar with the Fahrenheit scale. The Fahrenheit scale was defined, I believe, by 0 degrees being what temperature water in the Black Sea, not the Black Sea, but the Baltic Sea froze. Now, that's different than regular water. Regular water freezes at 32 degrees centigrade, which you're familiar with, and it boils at 212 degrees Fahrenheit. Okay? Now, the Celsius scale is different in that regard. 0 degrees Celsius is where water freezes, and 100 degrees is where water boils. So that tells us that 1 degree Celsius is different than 1 degree Fahrenheit. Roughly, you need 2 degrees of Fahrenheit in order to accommodate the same temperature change as 1 degree Celsius, or for that matter, 1 degree Kelvin. Now, 0 degrees Celsius also corresponds to 273 degrees Kelvin. Okay? Again, 0 degrees Kelvin is where all motion stops. All right? So the difference between 0 degrees Celsius and 100 degrees Celsius is something we would see, between, that change of 100 degrees is the same change that we would see in Kelvin. Although we would go from 273 degrees Kelvin to 373 degrees Kelvin. So as the chart here indicates, everything has a temperature, so everything emits light. The idea is this. If, as I mentioned before, if you have particles that are charged, like we do, and they move around, then they will accelerate. And remember what acceleration is. Acceleration is when you change velocity. And that means, what is velocity? Well, velocity has a direction and a magnitude. So if you are changing your motion, then you have a change in velocity, which means you have an acceleration, which means essentially the world knows about it. You have light being emitted. All right, so now everything doesn't emit in the same color. Okay, so for example, we have here a stop sign with white paint on it, and we have a fire going on, and so there's black here and smoke, and then over on this side we have different colors of the ocean here, and then we have ice, and we have, you know, this dirt in the background. Okay, so everything has different colors that we see, and the different colors are, as we know, a different wavelength, which means, you know, a different color for us, and that means it's also at a different energy. Now, there's a term here that is probably new to you, and it's called black body. And it's a theoretical construct, meaning it's a model that we use. A black body, imagine this. Imagine a box. It's basically black inside. So if you look at it through a little hole on one side, imagine a box completely covered up. It's painted black inside, and there's a little hole that you can see into. Okay, now take your eye away from this little hole, and there's going to be light that's going to be emitted in the outside of the world. It'll go through the hole, and it will populate the box inside. Okay, and so at some point in time, there'll be an equilibrium established between all the light that's in the box and the walls. And what you'll see on the outside is blackness, but if you measured the radiation, it would be coming out at a particular frequency. And that is what is being described in this picture here. Okay, we have the light intensity over here, or the energy density, and then over on this side we have the wavelength. So as I go up, you know, I'm getting to wavelengths that are more and more commonly observed, and then they decay away. So light having this frequency here that I'm measuring at the outside of that box is going to be less frequently observed than light over here. And then also, as I go higher in energy, there'll be less observation of light with wavelengths over here. Now imagine I heat up the box. Then what will happen is the light that's inside the box is going to get hotter, which means that the light is going to be more frequently observed in hotter regimes. So this whole curve is going to move to the left when it's hotter, and to the right when it's cooler. Okay, so this is that is actually the black body spectrum, and is actually a description of the Stefan-Boltzmann constant, or the Stefan-Boltzmann law. Now, Wien's law is characterized by this one: the hotter something is, the bluer it is. And we can see this with an incandescent lamp. Now, incandescent lamps are not lamps that are frequently available these days. You have to go out and look for them. But if you attached an incandescent lamp to a variable power supply, so you're able to change the amount of power that is going through the lamp, then you'll notice when you do this that the lamp starts at a very low intensity red color. And as you pump more power into the lamp, it becomes more red, and then orange, and then yellow, and then it becomes white. I don't know of any incandescent lamp that we can push to get to a blue color. So let me pause here and let me see if I can find on YouTube something to show. So let's continue. I couldn't find a very good YouTube video talking about Wien's law or just looking at an incandescent lamp. I'll try to make something with my cell phone and an incandescent lamp I have in class. But at any rate, what you'll find out is that I can start off with very, very low power going into the incandescent lamp, and it's going to be a very dull red. And then as I increase the power going into the lamp, then I'm going to get to a white light. Wien's law is characterized by what's going on with the temperature and what's going on with the peak here of this blackbody radiator. All right, now the idea with the incandescent lamp is that the lamp is has electrons going through this wire, and the electrons are being forced through the wire, and that causes the wire to heat up. And this heating up of the wire then allows, the relaxation, if you will, causes the light to be emitted. And we'll see more about that in a little bit. If I increase the temperature, then this peak is going to move. And this is where I see most of the light coming from. And when light is hitting my retina, I basically am seeing red light and blue light and green light and various colors. But I'm going to register an item in the background as being a particular color if more photons of a particular color hit my eye. So, everything is being emitted in a range of colors, but I recognize something as being blue if more photons from that object are blue rather than some other color. And so that's how I see particular colors. It isn't that everything is emitting light at a particular different amounts of radiation, but I recognize something as being blue if more blue light hits me. Okay? All right, so that's Wien's law. Now, the connection between temperature and wavelength is a very simple one. What I don't have here is this is lambda max is equal to a constant divided by temperature. So if I increase the temperature, then the wavelength associated with that light goes down. And on the other hand, if I decrease the temperature, then this number goes down. Then this number goes down, and this being a constant, then the wavelength goes up. And if you recall, gamma rays are very, very low, small wavelengths, very, very high energy. On the other hand, radio waves, which have a long wavelength, have very little energy associated with them and associated very low temperatures. Okay, so here is what the equation looks like. So lambda is a measurement of the size of the wave of light, and it's related to the temperature in this formula. So sorry about that. A nanometer is 10 to the minus 9 meters, so it's a very, very small thing. And let me remind you that visible light ranges from somewhere on the order of 450 nanometers to 750. So that ordering was blue 450 and red 750. All right, so here's an example of how you would do this calculation, and forget the fact that I didn't fix this lambda max should be equal to that thing. But if you put in something emitted at thermal radiation, so that's about 290 degrees. So if you remember thermal radiators or heaters and things like that, then the amount of wavelength associated with that is 10,000 nanometers. And then, that's indicative of, if you look in tables of or the previous charts that would associate wavelength versus the type of radiation, you would see that's well within infrared radiation. All right, so the next step would be for you to do a similar calculation and find out what is the temperature of a filament of an incandescent bulb, so at 950 nanometers. Okay, and then do the second question there. If the visible light is whatever it is, 400 and 700 nanometers, then where is most of the light from the light bulb going? Okay, and if you put your hand next to the light bulb, you can feel it's pretty warm. All right, the Stefan-Boltzmann law is characterized by this phrase. So heard of quite before. The hotter something is, the brighter it is. And we can see that with the incandescent bulb as well. So now the thing to concentrate on is, and I will show a video of this with the incandescent bulb a little bit later, is as I turn up the power rating, not only is the color changing, but as I go from dull red to orange to white, you'll see that it's really bright. It gets much brighter. Alright, so the thing with changing temperature, as the temperature rises, the spectrum changes in two ways. It gets brighter at all wavelengths, and the peak moves to shorter wavelengths, to higher energies. Okay, the spectrum, therefore, only depends upon the temperature of the object. Now, the spectrum doesn't depend upon the size of the object, although naturally, if I increase the size of the object, then the object is going to get brighter, okay? And the amount of power that I observe is going to get higher. All right, so the amount of power that you receive from an entity is dependent upon the temperature it is and the size of it. So that's characterized by this picture. This picture shows that if I had these objects all of the same size, so size is taken out here, then a human would radiate, energy in the infrared. After all, we are warm-blooded, and if you put your hand up on my skin or your own skin, you're going to feel some warmth there, as opposed to, say, somebody that's dead. They're just as warm as the environment that we're in. And then we compare that to the amount of power being emitted by a 3,000 degree star. Again, only the same surface area. Okay, so this star is of the same size as a human. Then it's putting out more power in the infrared region that we are in. Right? You see the red line here. All the power being emitted in these frequencies is much higher than what you see with the human, like of order of about 100 to 200 times. And then we go to a yellow star, like our sun, then it's emitting even more power, and it's overwhelming the power associated at the 3,000 Kelvin star. And then when we go to the blue star, it overwhelms them all. So no matter where I'm looking in the frequency or the wavelength, then the hotter stars are emitting more light than the lower temperature stars. So over here I have a blue star, right? Because it's putting out more blue light than red light. It's putting out more red light than the red star is. Okay, so the red star is putting out light here that is that we would observe as red for the star, because it's putting out more red light than blue light. For the yellow star, it's all across the spectrum, so I see more yellow, and my eye sees just as many red ones as blue ones, and then when we mix them together, then I correspondingly say it's yellow, right? Or really white light. Okay, so then we go to the blue star. It's putting out more blue light than red light. Okay, but the blue star is putting out more red light than the red star is. Very interesting, all of this. And yes, indeed, the stars have different colors. It's most easily seen if you have a green laser that you can point at these stars with. And you can point them at at different color stars up there, or different stars, and then you can compare your green laser with the blue stars and then with the red stars. It's kind of pretty amazing. Otherwise, our color vision is so bad at night that we basically just see white or dark. So here's an example. We can take a look at the night sky in these two pictures, and what is hotter? Is the blue hotter or is it the red hotter? Is the red hotter or is the blue hotter? Here's some red ones and there's some blue ones. Now, if you said red is hotter, then you would be wrong. The blue is hotter here, right? Just as we saw in the previous chart. The red is going to be hotter It's putting out more light. So that's basically Wien's law. Okay, now here is something different. Okay, here we have a blue ball, Neptune, and then we have a red ball, Mars. Which one is hotter? Now, this is sort of a trick question. The blue one is actually cooler. Now, some people would answer it because Neptune is so much further away than Mars. And that's partially true. But if you're actually think about it, where is the light source for both of these objects? Both of these objects are emitting light because light is being reflected off of them. They are not sources of light in a standard way, just like I am not the source of the various colors of my skin or my hair. No, you see me, or if you could see me, my students in my face-to-face classes see me, they see me because light is being reflected off of me. The source of that light is the light of, the incandescent or the fluorescent light bulbs in the classroom, or when you're outside, the sun, things like that. So these entities here are lit up because they're reflecting light that was sourced from the sun. Okay, so the sun is producing white light, and so the light that is hitting this is white light, but we only see red. The blue light is being absorbed somehow. We're not seeing that. And on the other token here, Neptune is absorbing the red light and allowing the blue light to be reflected off of it. So what is being absorbed? It's red here. Red is lower energy than the light that's being absorbed here, which is the blue. Okay, now the next step is to talk about the connection, the deep connection between light and atoms. Okay, so I'll pause here and we'll start up a new video to talk about this particular topic.